All right, so I'm going to talk to you guys a little bit tonight about L'Hopital's rule. I apologize for the kind of quirky angles and everything being far away. I've never done this before, not really set up to do this, but we'll see what I can do. So, all that L'Hopital's rule states is that if we're taking a limit of, I suppose a quotient of a function, you could think of it as, and whenever you plug in your limit, you're getting either 0 over 0, such as we would in here, right? If we have x squared minus 1 and x squared minus x, and I plug in 1, I'm going to get 1 minus 1, which equals 0, and then again 1 minus 1, which equals 0. If I get either this or infinity over infinity, L'Hopital's rule is applicable to the situation. It is not applicable if we have infinity over 0 or 0 over infinity, or pretty much anything that is not either of these two cases, okay? So, let's see here. So what we do now is we've got 0 over 0. So what we want to do is we want to take the derivative of the first function, the top function, which is x squared minus 1. That derivative is just going to be 2x, right? And then the derivative of the denominator function, which is going to be 2x minus 1, because we started with x squared minus x. So now, still taking the limit, as x approaches 1, plug it in, 2 times 1 is 2, 2 times 1 minus 1 is going to be 1, so it approaches 2. So if you plug that into a graphing calculator, you'll see that even though it would ordinarily make sense for it to approach some sort of infinity or some strange number, it's actually going to approach 2. All right, so now let's look at something a little bit fancier. Let me go back to some of these problems I have. So let's look at x, okay. We have the limit as x approaches, pi over 2 from the right-hand side, and we have the limit of cosine x over 1 minus sine, let me do that again, 1 minus sine of x. Okay, so if we plug in pi over 2 for cosine, we're going to get 0, right? Well, sine of pi over 2 is 1, but we have 1 minus sine of pi over 2, so we're going to get 0 again. So this is kind of an interesting one, because trig ones can be kind of interesting in that way, because we have to consider which side we're coming from here, okay? So first let's take the derivative of cosine of x, which is going to be negative sine x, right? Negative sine of x. And then 1 minus sine x is going to be, this one's going to become 0. Sine x would be cosine x, but we have negative sine x. So we have negative sine x over negative cosine x. Obviously our negatives cancels, so we just get sine x over cosine x. And the limit as this bad boy goes to pi over 2 from the right-hand side. So what I like to do is I like to, you can draw it out if you'd like. What I prefer to do is draw, because these are tricky for me. I have to really think about this one. I'd draw something that's like a unit circle like this. And because so this is pi over 2, right? Let's say this is 0. We're coming at pi over 2 from the right-hand side. So that's right hand on a graph, right? So that means we're coming at it from this side, which on a unit circle means we're coming at it from the I guess you'd say counterclock, or we're coming at it clockwise, right? So we're coming at it from values bigger than pi over 2. So anything bigger than pi over 2 is going to make cosine negative, right? Well, I should say anything between pi and pi over 2 is going to make cosine negative, right? So we know, and it's going to go to 0, but from the negative side. And then, so we're gonna call that kind of negative 0. And then sine, as it approaches pi over 2, is going to go towards 1, right? So anytime we have this sort of thing, anytime your denominator is going towards 0, your limit is, it's infinity, right? So, but this is a negative 0, so it's going to be negative infinity. Hope that makes sense. So let's see here. That's kind of a tricky one. I would definitely encourage some sort of visual. For me, I prefer the unit circle. Some people might prefer kind of graphing it. They're just tricky. They're just tricky that way. Okay, so now let's take another one. So let's do this one. This one looks real fancy. We have t. This t goes to 0 of e to the t minus 1 over, I'm sorry, I'm getting in your face, t to the 3. Okay, so don't be frightened by the t's. It's just our independent variable. We treat it exactly like an x. So if I have e to the t, right, so as t approaches 0, anytime anything goes to 0, anytime we raise a number to the exponent of 0, we're going to get 1. So we have 1, and then we still have this minus 1, right? So we get 0. And then we have 0 to the 3, which is also going to be 0, right? 0 times 0 times 0 is going to be 0. So, no good. L'Hopital to the rescue. So, what we need to do is take the derivative of this top function. So, the derivative of e to the t is going to be e to the t. It's cyclical that way. The minus 1, it goes away, right? T to the 3, that's going to become 3t squared, right? So now, let's plug in 0 again. Let's see what happens. Well, e to the 0 is 1. 0 squared times 3 is going to be 0, right? So that goes to positive infinity, right? Okay, just want to check myself. So, that's the basic idea. I'm going to go ahead and work one more, just because it looks like a snazzy one that I'm looking at. And then I'll kind of go over some of the other cases. This is going to be ln of x over square root of x. Okay, so now let's see here. Okay, we're seeing as x goes to infinity though. So here what we need to do is, well, what happens to ln as x goes to infinity? It just goes to infinity, right? Because we're saying e to what power equals infinity? Well, e to an infinitely large power would equal infinity. So we're going to have infinity. Well, what's the square root of infinity? What times what equals infinity? That's going to just increasingly get bigger, right? So we're going to have infinity over infinity. So now, what if I have, well, I guess I shouldn't say that we just know that we have to take the derivative. So, derivative of ln x is 1 over x. I'm going to think of it this way. Derivative of square root of x is 1 over 2 square root of x. So what this really becomes is 1 over x times, sorry, that looks like alpha, 1 over x, that still looks like alpha, 1 over x times 2 square root of x over 1. Let me rewrite this. Okay, so now let's try this again. So we plug in infinity. Okay, so we have 2 times, we have 2 times square root of infinity, which is just infinity, right? The 2 just gets swallowed up. It doesn't even matter at that point. And then x infinity. Oh, well, we still have infinity over infinity. So what do? We do it again. Okay? So now, derivative of 2 square root of x is going to be 2 over 2 square root of x. Square roots cancels. So it just becomes 1 over square root of x. And then over the derivative of x. Well, that's 1, right? So now what we have is 1 over, we can ignore this 1 as the denominator, right? Makes no difference. So now we have 1 over the square root of x as x approaches infinity. Well, what's that now? That's just 1 over infinity. Anytime your denominator goes to infinity, our limit is 0. So now what I want to do, this is actually a great way to do it, is I want to talk about some of those cases. So if we have something like, right, 1 over infinity. Any number over infinity is going to be 0, right? Because we're taking this number, it doesn't matter what number it is, it could be 1,000, doesn't matter. And we're cutting it up into infinitely small pieces. So obviously the value of those pieces, each piece is going to get increasingly small, right? So it's going to go to 0. So now we have, let's see here, as any time your denominator goes to 0, you have infinity. Well, let me do this. Equals 0. And then 1 over 0 equals infinity. So it's kind of a similar reason, it's just the inverse there, which is that we're cutting up 1 into increasingly, well, let me see here, an increasingly small number of pieces. So it's like, I'm sure this is common sense to most people. I just want to make sure I'm thorough. If we have the typical idea of a pie, like for a fraction, and I cut it into 4 pieces, and then I cut it into, the piece is only going to be yay big, right? And I cut it into 3 pieces. Now this is my slice, it's getting bigger, right? And then I cut it into half, it's getting bigger and bigger, cut it into 1 piece, it's getting bigger and bigger and bigger and bigger. So the fewer pieces I cut it into, the bigger the value is of each, right? So that's why. That's going to work out that way. Okay, so now let's look at something. If we have, rather than the quotient of 2 things, sorry, I'm trying to find a problem. Perfect. Rather than the quotient of 2 values, the product of 2 values is x approaches infinity of, let's actually do this. Let's do this. So x approaches negative infinity of x squared e to the x. Well, what do we do? L'Hopital's rule specifically works for quotients of functions, or ratios of functions, however you'd like to look at it. So we have to get a little bit more clever. It's actually not that complicated, though. We just have to write this as a quotient. So this is like saying x squared divided by, and you can do this 2 different ways. E to the negative x, right? Well, I guess I shouldn't say you can do it 2 different ways. But this is going to be the same thing, right? So we're just finding a way to get this guy right here in as a denominator while not changing the value at all, which that doesn't change the value at all, right? Because we made this negative, so e to the x, if we make this e to the negative x, let's see here. E to the x equals 1 over e to the negative x. That's kind of the idea. If you don't know that, if you don't remember that, that's a really helpful thing to know here. So now we have it in the quotient form. So let's see here. So now we're looking at it as it approaches negative infinity. Well, what happens to x squared as it approaches negative infinity? You have this. Think of it that way. So what do you get? You're going to get a positive infinity, right? So now you have e to the negative x. So that is e to the negative infinity, right? So that's the same thing as e to the positive infinity. So I can do this, e to the positive infinity, which equals infinity, right? So, no good. So we have to take the derivative of both of these guys, right? So the derivative of x squared is going to be 2x. That's pretty elementary. And then the derivative of e to the negative x is going to be negative e to the negative x. So now let's try that again. So 2 to the 2 times negative infinity is just going to be, again, the 2 gets swallowed up by the infinity. So it's just going to be negative infinity. And then we have, again, we have negative e to the negative infinity, which is the same thing as negative e to the infinity, which becomes negative infinity, right? Negatives cancel out. Infinity over infinity yet again. Okay, so now we need to take the derivative again. Derivative of 2x is going to be 2. The derivative of negative e to the negative x is going to be e to the negative x. So, same thing. So now we're saying, okay, what happens as this becomes, as this goes to infinity? You have 2 over e to the negative infinity, right? So that's e to the positive infinity, which is infinity. So we have 2 over infinity. Well, if you remember what I was saying a second ago, you'll know that we're taking 2 and we're cutting it up into an infinitely large number of pieces, meaning that each piece becomes smaller and smaller and smaller, going towards 0. Okay? So that's how you want to do those problems. They're relatively simple once you get the hang of it. In my opinion, the hardest part is going to be the trig functions and or doing things, taking limits as something approaches it from the right-hand side or the left-hand side, very specific sides like that. Or things like this where you come across a product of two functions rather than a quotient, which is a relatively easy fix. You just want to basically invert the second of them, right? So I inverted this and made it 1 over e to the negative x, because it has to be the same function still, right? So yeah, I just invert it and then I divide by them. Hopefully that makes sense. Okay, go ahead and message me if you have any questions or anything like that. Hope this has been helpful.